Hello, my name is Liam Pocher and I'm from Los Alamos National Laboratory. Today I'll be talking to you about the results of a perturbative technique that is used to observe nonlinear effects and asymptotic convergence to a full nonlinear solution in the context of the modified Euler equations. The asymptotic convergence is used to predict a lower bound calculated by perturbation truncation error in the differential system. Some brief theoretical description of the Euler equations, the terms used to modify the standard Euler equations, and the perturbative technique shall now be discussed. As many of the audience probably already know, the Euler equations form a hyperbolic partial differential system that describe conservation of mass, momentum, and energy in the context of equilibrium maximal Boltzmann statistic-obeying fluid dynamics. In addition to the standard Euler equations, irreversible parabolic terms associated with viscosity, momentum diffusion, and heat conduction, energy diffusion, are included within our analysis. This analysis is simplified by considering 1D planar fluid flow. The differential system submitted in the previous slide may be massaged to ease mathematical and numerical treatment. Non-dimensional variables may be introduced corresponding to independent space and time and dependent flow velocity and thermodynamic state variables. Familiar non-dimensional ratios, specifically the Reynolds and Peclet number, are obtained. Other non-dimensional ratios, K sub E and K sub M, are defined. An equation of state is used to relate thermodynamic variables. Finally, we point to the box non-dimensional differential system in the lower right corner of the slide, which is the one analyzed within this work. However, our theoretical treatment is not yet complete. The perturbative technique utilized within this work may be written as the expansion of some variable phi in an exact power series containing n+1 terms, where n is the desired order of the error introduced when the differential system has higher order terms omitted. See the equation for an arbitrary variable phi in the middle of the slide, where phi may be set equal to some initial value plus the sum from 1 to n of some new variable zeta. This new variable zeta becomes a quantity that is solved for in the differential system. In our context, the arbitrary zeta variables are eta, v, and epsilon for the mass density, flow velocity, and specific internal energy density, respectively. These new variable definitions may be inserted into the differential system on the previous slide. We obtain the expanded differential system in the bottom right of this slide, shown here. A table at the top right of the slide shows sample amplitudes for the perturbed variables at various total perturbative amplitudes. The perturbed non-dimensional differential system from the previous slide may be massaged into a form where solely a first-order time derivative is on one side of the equation and all other terms, including spatial derivatives, are on the other side. These functions, f, g, and h, are the equations that are calculated and then solved numerically to produce a semi-analytic solution. Two different order perturbations were used, a quadratic and a cubic. These solutions were compared to a fully nonlinear differential system solved on the same length and time scales. The initial conditions fed into these variables are detailed at the bottom of this slide. Note, though, that the introduction of new variables does not in and of itself introduce error. Only the truncation of those highest order terms in the explicit differential system introduces error. How can we know to trust the solutions that have been deployed by the numerical algorithms? A comparison to a well-vetted, robust finite element code has been done in order to compare performances. Results of this may be seen in the figure to the right. Fifth-order convergence as well is observed for a comparison of a deployed finite difference code solving the full nonlinear differential system treating as an analytic solution a much more highly resolved simulation from the same code. Now that we have a well-verified semi-analytic solution, we may observe and compare error from various perturbed differential systems. In addition to comparing to a highly vetted code to ensure our semi-analytic solutions are performing well within the fully nonlinear differential system, the quadratic and cubic order perturbed differential system solutions may be compared to each other. This comparison allows us to compare how well predicted truncation error matches actual truncation error. In general, the order of the truncated terms in the differential system is n+1, with n being the order of the expansion. A contour plot of this error, in addition to performed simulations shown with purple points for the quadratic simulations and colored points shown for the cubic simulations, may be seen in the left of this slide. Note the order to which a perturbation must be taken out in order to obtain desired accuracies. Looking at the type right graphic, you may note that within the semi-analytic results there are three sources of error. Error from the spatial discretization, error from the temporal discretization, and error from the truncation of terms in the perturbed differential system. Two of these errors come solely from the given numerical operator, the spatial and the temporal error. The error from the truncation of higher order terms may be calculated by comparing a quadratic to a cubic simulation. See the bottom right plot. For low resolution, the numerical operator error is still present. However, as the numerical resolution becomes finer, error from the perturbation expansion is still present and begins to dominate. These quadratic and cubic simulations were performed with perturbative amplitudes of 0.01. The error from the quadratic expansion may be calculated to be 0.01 raised to the third power, which is 1 e to the minus sixth. This value is indeed the error we observe in the residual perturbation error. Various numerical results may now be shown. At the top of the slide, two figures and a table are replicated from prior slide to provide visual cues. The bottom of the slide contains three figures showing results for the quadratic and cubic perturbed differential systems in the fully nonlinear differential system. These three different families of solutions have four different simulations, each corresponding to viscosity and thermal conductivity being turned off or on. The Reynolds number and Peclet number were set to either 100 or infinity to approximate for finite or vanishing viscosity or thermal conductivity. Note that no matter the size of the perturbation that is superimposed on the flow, the overall structure of the solution varies as the Reynolds number and Peclet number are changed. The non-causal behavior of the irreversible terms is evident from the structure of the solution. As the size of the perturbation increases, the approximation of the quadratic and cubic solutions becomes less valid. See the figure at the top right. For delta phi of 0.01, we have excellent agreement as the solutions lie on top of each other. For delta phi of 0.1, we may note that slight difference away from the fully nonlinear solution is occurring, while with a delta phi of 0.55, we note significant divergence. However, the higher order cubic solution slightly bridges the gap between the quadratic and the fully nonlinear differential system solutions. The figure at the top left shows that much higher order terms would be necessary in order to obtain an accuracy commensurate with lower order perturbations. However, there is a drawback associated with this technique due to the fact of the tedious yet algorithmic algebraic manipulations necessary in order to derive the highest order perturbed differential system. At higher order perturbations, asymptotic convergence is observed. Shown on the slide are two different plots excised from a previous graphic. The viscous and the viscous conductive solutions are shown. The black solutions are the fully nonlinear, the purple is the quadratic, and the colored solutions are the cubic solutions. Note how the purple and colored solutions asymptotically decay down to the fully nonlinear solution. As the order of the perturbed differential system is increased, the produced semi-analytic solution is progressively collapsing down onto the fully nonlinear differential system solution. As noted previously, higher order terms would be necessary in order to observe a perturbed differential system solution being coincident with the fully nonlinear solution. This presentation has explored a perturbation technique in the context of the Euler equations that have been modified with the inclusion of irreversible, non-causal, viscous, and heat conduction terms. The theory describing these perturbations and an algorithmic technique for deriving the perturbed differential systems has been detailed. It has been shown that the lower bound on error between successive perturbations is of a predicted value. See the plot at the bottom left. Asymptotic convergence for varied solutions has been shown as well, and we may predict to what order a perturbative solution must be taken to obtain desired accuracy. Possible future avenues for this work may including different diffusive effects, and analysis of other differential equations to observe different behavior recovering various nonlinear effects. On this slide, we note the references that were used within this work. Acknowledgement of the individuals without whose work these results would not have been possible, and the funding agencies supporting this work. Thank you for your time. I hope you enjoyed this presentation.